Hello friends, in today's class we will see process scheduling. Under this process scheduling we will first see some basic concepts, then we will go to some scheduling algorithms. Okay, see, this CPU scheduling is a basis or some foundation for multi-programmed operating systems. See, CPU scheduling is a foundation for a multi-programmed operating system. By switching this CPU among n number of processes, so the operating system can make this computer or CPU more productive or optimal. So it means that operating system can optimize these or make best utilization of this CPU. So when it uses CPU switching from one process to another process. See here, the switching of CPU is nothing but allocation of CPU from one process to another process. That switching the CPU meaning is simply the allocation of CPU from one process to another process when there are n number of processes in a CPU. By switching this CPU among n number of processes, the OS can make the computer more productive. Okay, the OS can make best use of that computer. So now let us see some basic CPU scheduling concepts, and then we will see some scheduling algorithms. So operating system which supports threads. These threads are called as already we know that is kernel threads. So they are not processes. These kernel threads are scheduled by operating system. The kernel threads, keep it in your mind, the kernel threads always scheduled by operating system itself, because kernel level threads are supported by OS itself. The terms process scheduling and threads scheduling are similar, but sometimes we use these terms or words process scheduling and thread schedulings interchangeably. It means sometimes we may use the word process scheduling and sometimes we may use thread scheduling, particularly when we discuss general scheduling concepts. Then we should use always the term process scheduling. Whenever we use or whenever we discuss thread specific concepts or thread specific ideas, at that time we should use the word thread scheduling. Okay, so in a single processor system only one process can run at a time. Already we know this one. Other processes have to wait until the CPU becomes free and they can be rescheduled. So the main objective or main primary goal of this multiprogramming is to have the main objective of this multiprogramming was it is to have some processes, okay, some processes running at all times to make best use of this CPU. The main primary goal of this multiprogramming is to have n number of processes, okay, in a same CPU, and those all processes should be keep on running all the times so that we can take best use of that CPU. Okay, the idea is very simple here. A process is executed until it must wait. It means that if the process does not want to wait, it will be keep on executing, typically for completion of some input output request. So usually processes will be keep on executing. So when they want to wait, they will usually wait for a completion of some input output request, because right now the the process is using the CPU, but after some time the process may want to use this input output devices. So if the input output devices are busy in some other tasks, at that time that process has to wait for this input output request. So because of that only, if the process is running or executing in CPU, the CPU is allocated for that process. Once that CPU is detached from that process because of completion of process execution, that process wants to use input output devices. Now at that time, if input output devices are not available for this process, then that process has to wait for this input output devices. In a simple computer system, the CPU then sits idle. All this waiting time is wasted now. no useful work is accomplished. So with multiprogramming we try to use this time productively. We may not use or we may not waste the time here. Okay, so we may not use the time, we may not waste the time here. Okay, uh, in simple computer the CPU sits simply idle, so even that other processes wants to execute, but this multi-programmed system, since it is running n number of processes, the one if one process starts to wait for input output devices, another processes can execute in a processor or a CPU. Okay, so with multi-programming what we can do, we try to use this time productively. We should not waste the time here in waiting for any other input output devices. So many processes are kept in a memory at one time in multi-programming systems. When one process has to wait, the operating system takes that CPU away from that process and gives that CPU to another process. So you just imagine one process is waiting for input output devices. At that time the operating system takes the CPU away from that process and it gives that CPU to another process. This pattern keep on continues. Okay, so then every time one process has to wait, another process can take over the use of that CPU. Okay, so if one process is using the CPU, the remaining processes have to wait for CPU. Okay, then scheduling of this kind of this operating system functions is a scheduling process. Scheduling of this kind is a fundamental operating system function. This is a main basic function of operating system. Okay, so almost all computer resources are scheduled before they use. So computer resources are nothing but input output devices and any other components of a CPU. Okay, these all input output devices and components of CPU are called as resources of a computer. These all resources should be scheduled before we use those components of computer or this input output devices of computer. The CPU is, because of that only, the CPU is, of course, it is one of the primary computer resources, which is a main resource of a computer. First we have to schedule this resource, that is CPU. CPU is also a resource. We have to schedule this CPU. So therefore its scheduling is primary goal for this operating system design or the designers of operating system. Now we will see the cycle. Which cycle? CPU burst or input output burst. Burst is nothing but the process, if it is using CPU right now, suddenly after its execution, suddenly it starts to use input output device. So here this CPU is also one resource and input output devices also resources of a computer. Once the CPU is switched from one process to another process, so suddenly it shifts from one process to another process. This is called as a burst, CPU burst. So once the input output device is allocated for a particular process, after its accomplishment of work, that process can leave that input output device and that input output device can be allocated to next process. So suddenly it happens. So once this switching happens from one process to another process, it may be CPU switching from one process to another process, or it may be input output device switching from one process to another process. This sudden change from one process to another process is called as burst. Okay, process execution consists of a cycle of CPU execution and input output wait. The processes will be alternate between these two states. Which states? Execution state or else wait state. The process execution begins with the first CPU burst. This is followed by after CPU burst, obviously there will be input output burst. Again after this input output burst, obviously there will be again CPU burst. After this CPU burst, again there will be one input output burst, like this. Okay, the final CPU burst ends with a system request to determine or to terminate that execution. So this input output burst cycle is shown in this figure here. See, you can see here the instructions are executing here: load, store, and add, store. Okay, load, store, add, store, and read from the file. After that, when these instructions are executing, the process is using CPU. Okay, this is CPU burst. Okay, now suddenly that process wants to wait for input output. At that time, this is suddenly changed from CPU to input output device. So this is called as input output burst. Once it completes the input output device work, then again it wants to use CPU. In that CPU, it starts executing storing some instructions like store, index, and write to file, like this. So during this period, it is called as CPU burst. Okay, so once again that process gets the chance to use input output device, then it has to wait for that input output device. That time is input output burst. After input output burst, now the process wants to again use a CPU. This is called as CPU burst. So this is the time taken by the process to use a CPU is a CPU burst, and time taken by the process to wait for input output device and to use those input output devices input output burst. Okay. Now next, one more small concept is there, that is CPU scheduler. Whenever the CPU becomes idle, the operating system must select one of the processes in the ready queue to execute. Okay, so once the CPU becomes free and it does not have any processes to execute, at that time operating system has to take one process among n number of processes from the ready queue. Okay, the selection process, which process, because there are n number of processes are there, which particular process that operating system should take or select to be executed to execute that process, which is completely carried out by a CPU scheduler. It depends on, it does or it is done with, it is done by the CPU scheduler. CPU scheduler is also called as short term scheduler. Okay, the scheduler selects a process from processes in memory that are ready to execute and allocates the CPU to that process. Okay, note that the ready queue is not necessarily in, first out. That is a FIFO queue. The ready queue can be implemented as a FIFO queue, a priority queue, or else it may be a tree, or else it may be a simply an unordered linked list also. It means that the in queue there are n number of processes are there. So as I already told, OS has to select any one process among those n number of processes, and CPU should be allocated to that process, on which basis this process is selected. So this process is not selected not only on first in first come or first in first out queue, or else it is not compulsorily FIFO queue. It may be FIFO queue, or else it may be priority queue, or it may be a tree, or it may be simply an unordered linked list. All these processes in the ready queue are lined up in a waiting for a chance to run on a CPU. It means these all processes are waiting for a CPU to be executed. Okay. So preemptive scheduling and non-preemptive scheduling, two concepts are that, try to differentiate clearly here only. So CPU scheduling decisions may take place under the following four circumstances or four situations. CPU scheduling decisions should be taken in these four situations. When we should take CPU scheduling decisions: when a process switches from running state to waiting state. Okay, when a process switches from running state or executing state to waiting state, we have to take a decision of CPU scheduling. It means that this time the process is switched from execution state to waiting state. So earlier it was executing in CPU, now it is waiting for input output devices. Now the CPU should not sit idle, so because of that only that CPU should be allocated to some other process, and so because of that only we have to use here CPU scheduling. Second situation is when a process switches from executing state or running state to ready state. So already it is executing in a CPU. So once it completes its execution, then it changes its state to execution or running state to ready state. So ready to use the input output device or any other resources. At that time CPU is again free, that CPU should not sit idle, so this operating system will allocate this CPU to any other processes. Third situation is when a process switches from waiting state to ready state. So when the process is waiting for input output device or any other resources, once it completes its waiting state, then it gets its chance to use that input output device or CPU or any other resources. And if it gets a chance, it has to enter into ready state. It is ready to use that input output state. So out of this waiting state, now it enters into ready state. At that time also we have to use CPU scheduling. And fourth is when a process terminates. Once the process completes its job or its task, then completely it terminates. So at that time also system or CPU should not sit idle. Because of that only CPU should be allocated to next processes. So in these four situations or circumstances we have to use scheduling. Okay, a new process, okay, for situations or circumstances 1 and 4, that is first and last, there is no choice in terms of scheduling. Okay, so we have to schedule the CPU. A new process, if one process is existing in a ready queue, must be selected for execution. Okay, so a new process should be selected for execution once the process terminates, and there is no choice, there is a choice for situations 2 and 3. So here we have to we have choices for situation 2 and 3, but for first and fourth situation we don't have any choices. When scheduling takes place only under circumstances or situations first and fourth, we say that the scheduling scheme is non-preemptive. Non-preemptive means CPU is not shifting from one process to another process, or cooperative, otherwise it is a preemptive. So it means that preemptive is nothing but one process is there and it has not yet completed its complete execution. So after that it starts to wait for input output device, and once it completes the input output device, till that any other process can utilize this CPU. Once that first process completes its input output device task, it again comes back and it can again takes the CPU, or again it can use the CPU. So like this, if a process is utilizing any resource like CPU or any input output device, then it is called as preemptive. Okay, if a process is not coming back to CPU, then it is non-primitive. Okay, so under non-primitive scheduling, once the CPU has been allocated to a process, the process keeps the CPU until it releases the CPU, either by terminating or by switching to the waiting state. Okay, in non-preemptive scheduling, if a CPU is allocated to a process, that process will keep that CPU with it only until it completes its execution. That is non-preemptive. But in preemptive, if a CPU is allocated to a process, it does not keep that CPU all the time. So whenever it wants to execute input output device task, it takes or it uses input output devices, and it again completion of input output devices, it can come back to CPU. So like this preemptive and non-preemptive scheduling algorithms are there. So preemption also affects the design of this operating system kernel. Yeah. So next small topic is a dispatcher. Dispatcher is nothing but it is a module that gives the control of CPU to the process. selected by the short term scheduler. Okay, this function contains again three sub functions: switching context and switching to user mode and jumping to the proper location in the user program to restart that program. So the dispatcher should be fast, and since it contains invokes since it is invoked or called during every process switch. Okay, so whenever a process is switching from or CPU is switching from one process to another process, this dispatcher is called or invoked. Okay, so just imagine once a CPU is completes execution of a process, and now that process will be terminated, or the CPU will be given or allocated to next process. At that time when CPU takes the next process, this gap should not be longer. It means that the time after the completion of a process execution till the beginning of next process execution should not be long. So this gap should be very small. The time it takes for the dispatcher to stop one process and start another process to execute or running is known as dispatch latency. So this dispatch latency should be always smaller. Now we will see some scheduling criteria based on which aspects we are going to categorize these or we are going to categorize these scheduling algorithms. Different CPU scheduling algorithms have different properties, and the choice of this particular algorithm may depends on some criteria. So in choosing these which algorithm to use in particular situation, we must consider some properties of these algorithms. So many criteria have been suggested for comparing these CPU scheduling algorithms. So these scheduling criteria are used to compare the scheduling algorithms, and based on your requirement you can use the suitable scheduling algorithm. So which characteristics are used for comparison, we are going to see now. The criteria includes these following things. First criteria is CPU utilization. So we want to keep this CPU as busy as possible always. CPU should not sit idle. Okay, CPU utilization should range from, or it may range from 0 to 10%. Okay, 100% utilization is always best. In a real system it should range from 40% to 90%. Okay, so throughput is a second criteria. If the CPU is busy in executing processes, then work is being done. So one measure of work is a number of processes that are completed per time unit is called as throughput. If it is throughput is important for you, then you have to use the scheduling algorithm which is giving importance to this throughput. Okay, for long processes this rate may be one process per hour, and for shorter transactions it may take only 10 processes per second. Okay, for longer processes it may take 1 hour to execute one process, or for shorter transactions or for shorter processes it may execute 10 processes or 20 processes in a single second. Okay, then turnaround time is nothing but it is a time interval from the time of submission of a process to the time of completion of that process. It is a turnaround time. It means once a process enters the processor or CPU and it starts its execution, and sometimes it may need to wait for CPU, or it may need to wait for any input output device, and again it comes back to CPU and start its or resumes its execution. Like this it can keep on switching from CPU to input output and input output to CPU. Like this ultimately it completes its execution, and the time taken by the process once it enters into the CPU till the completion of its execution is called as turnaround time. Waiting time is the sum of periods spent waiting in the ready queue. The amount of time spent by the process to wait for a CPU or to wait for a input output device is a waiting time. Then response time. So response time is nothing but, okay, so time it takes to start responding, not the time it takes to output the response. So in an interactive system, turnaround time may not be the best criteria. Usually a process can produce some output fairly early. It means some processes produce the output very soon and can continue the computing new results while previous results are being output to the user. So therefore another measure is the time from the submission of request until the first response is produced. So this measure is called as response time. Okay, the time it takes to start responding. Okay, so the turnaround time is generally limited by the speed of, or limited by or restricted by the speed of output device, because some output devices may be fast and some output devices may be very slow. So depends on this speed of input output devices or output device, the turnaround time is restricted or limited. Okay, it is necessary to maximize or to increase, it is necessary to increase the CPU utilization, and it is necessary to increase the throughput, and it is necessary to decrease the turnaround time, waiting time, and response time. So among these five criteria, CPU utilization should be more, throughput should be more, and turnaround time, waiting time, and response time should be less. Okay, in next class we will see scheduling algorithms.